today I'm going to start a really big topic. It's going to be a whole little branching series off of the N64 assembly. We're going to dig into exceptions and interrupt handling. This is really where assembly language gets to shine. This is where we you almost have to write assembly. You can kind of start to do things in a higher level language, but really this is where you have to do it right. So we're going to see some of these things. It's going to be pretty involved, but our goal is to create a generic exception handler for use by any N64 developer. Even though this is written in assembly, it will be usable from C code, and we will get to that at the end. Exceptions and interrupts. They're hardware events that allow software to react. That's it's a yeah, that's it. It's a hardware event. So exceptions and interrupts. I'm going to jump down here. The difference between an exception and an interrupt. While the words are interchangeable, in most conversations, especially regarding MIPS. Other architectures can use them a little bit differently. The code to handle them, especially on MIPS, is intertwined. And we're going to see a lot of that. And we're going to have to kind of take it apart and figure out which ones happened. The difference. Exceptions happen inside the processor itself. And then interrupts happen on the circuit board and toggle a pin to notify the processor that something happened that needs a response. So as part of this project, so here, let's, over here, so as I said, exceptions are inside the processor, interrupts are outside. And so this is a user-created schematic of the Nintendo 64 main board for revisions 03 and 04. It doesn't really matter, and this isn't a definitive, perfect schematic, but it's going to really help us explain this. So if we look along this edge, right here we can see interrupt 0. And that is a pin, and I'm going to try and carefully follow this, and it's kind of hard, your eyes, yeah. Oh, I got it there. All right, so basically, and I've lost my line again. Basically, it connects to the RCP, which is this big chip, RCP NUS. And so that's int 0. The other thing that I'm going to point out is here's int 1, and we can see we kind of have to follow it around, but these are really all tied to I think they're pulled up VCC. So those cannot be toggled. Or int 1 cannot be. So we're going to look and keep looking around the edge here. And we're looking for int 2. Now int 2 is another one that is used. And this line goes all the way down, following this edge here, because it goes a long way away here. Int 2 comes all the way up, and it's right here. And we can follow that, and it goes and connects into the PIF. So I can tell you in advance that this pin, what happens is when you hit the reset button on the console, it doesn't immediately do a reset on the CPU and RCP. And that seems a little surprising because that's what a reset button does. But what it does on the N64 is this is the schematic for the reset button, and it ties to a pin on the PIF. So once that button is pressed, the PIF actually triggers the interrupt to the CPU, and then waits half a second, plus or minus. I'm not sure exactly how accurate that is, but a half a second. And so it sends the interrupt to the CPU, gives the CPU up to half a second to do whatever it wants to do, knowing that there is a hard reset pending. And after that half a second, the PIF will actually do this NMI CPU or cold reset. I'm not sure which one of those, but or here's the output reset. So basically, the PIF is going to perform that hard reset of the console. Now, that half a second is actually a good amount of time, and it gives the games an opportunity to save any values that are needed to avoid save game corruption, especially if it was in the middle of a save when the gamer hit the reset button. Once again, just trying to make sure that players have that best experience possible. So that's interrupt 2 on the CPU, and we are going to be handling that. Int 1, so int 0 is the RCP, int 1 is not used, int 2 goes to the PIF, and we keep looking down this edge. Oh, that's the RCP. Keep looking down this edge. That was the int 2. And there's int 3. And again, it's just pulled up, I believe. VCC, I believe, is the pull up. VSS is ground. So int 3 is not tied to anything, and we keep following around, and we get to int 4, and again, that one is the same, pulled up onto VCC. So those interrupts are not used here. What makes those kind of interesting is that some of the debug hardware that was available for official Nintendo developers would use some or one of those interrupts to force the game into a debug mode or something like that. So technically those pins will work, but you're gonna have to get out a soldering iron and melt the solder on the pin and lift it up and tie a wire to it, and more involved than what most of we want to do, but we'll see that it's not that hard to go ahead and account for those so that somebody else could do that and use our exception handler for that. So that'll be kind of interesting. So let's see. Now, exceptions and interrupts versus polling. Polling is when your code spins in a loop, waiting for a bit to change or some other event to occur. That's not the best use of your code, especially on a system with, not a lot of resources. You don't want to sit around waiting. You want to always be doing work. So that's where exceptions and interrupts come in. And so it gives you a chance to create just a little routine, a little function, and assign it so that when this event occurs, you can respond accordingly. And we're going to see some examples of this. We're going to develop the examples. So the other thing that really makes this so useful and valuable is that MIPS offers precise exceptions. The CPU knows exactly where the error is and can provide the details about the error. So in the exception handler, you're going to have all of the information that you need in order to possibly fix the error, to fix the situation, or sometimes all you want to do is skip over the error and just ignore it, and that's okay too. We'll see there are some of those exceptions and interrupts that you do want to actively ignore, but there are many that you just need to respond, just need a little bit of work done at that time. One of the notes about writing an exception handler is really you want it to be pretty minimal, because you ideally you don't want to have enough code where you actually cause an exception inside of your exception handler, because then you start to get into a Stack Overflow situation, or it just gets a lot harder. So the goal is to always write very small interrupt and exception handlers. So we're going to move on to some assumptions. We've got a good list of these too. So we are going to be writing some really optimized assembly. We really care about how it's laid out. It's going to be some interesting stuff here. So the N64, that main CPU, it by default operates in 32-bit kernel mode. Now, this is going to be a little bit more... I'm going to flip over to the data sheet and show you why, but first we're going to talk about these. So, not in 64-bit mode, not in user or supervisor mode, and I want to point out that in 32-bit kernel mode, 64-bit instructions work fine because it's kernel mode. And I'm not sure why they decided that 64-bit instructions required kernel mode, but that was the MIPS architecture. So 64-bit adds, subtracts, multiplies, all those things work great in 32-bit kernel mode. Now, the other thing is kernel mode is required for coprocessor 0 access. And that's a lot of what we're going to be doing as well, because coprocessor 0 is really how the MIPS processor is controlled. And that's where all of our exception details from our precise exceptions, all of the details about the error are stored in coprocessor 0 registers. So we're going to see a lot of those. Now, the next thing here is in the MIPS ISA IV version 4, it defines up to 4 exception or interrupt handlers. There is a fifth that's the reset vector. That's the other term for these memory addresses, is a vector. And so 8,000 is the base range. TLB is it's advanced memory management stuff. It's a cool feature. It's used by just a few games. We're going to see a little bit of that. We're definitely going to learn how to handle those. And then the XTLB handler is 80 hex later, and this only applies in 64-bit mode. So once again, we are in 32-bit mode, so not relevant for us. Then there's this cache exception handler. Now, the N64 definitely has a cache, both for instructions and for data, but in this case, it's not going to trigger an exception handler. So that was the choice made on this specific model of MIPS processor. Many others do have that, and so we'll see that. And then the general handler is down at the 180. Now, this is the one that's going to do most of the work. And so it's going to have most of the code and we're we're going to spend a lot of time there, but it's still cool. It's going to be fun. So we do not need these two. We only need the 00 and the 180. One of the interesting things to note is that the PIF, which is how the console starts up, is it writes out some really handy variables in this memory range, the 8300 to 31C. And we want to be very careful and leave those alone, but you see that these are kind of in the middle of our range. So we're gonna have some code that starts here. We're gonna have some more code that starts here, and game code may start as early as this 400, but there's this little gap between the 31C and the 400 range. So 228 bytes, 57 words. That's 57 MIPS assembly instructions. So we can do some good work with that space. But we are going to we're going to use the 0 up to the 400, and we're just going to exclude this range. So let's take a quick look at the kind of things that are stored there. Oh, and I closed it. There. Cool. Have the link handy. So this is in the at address 300. Almost all of these are 4 bytes. And so if there is a 1 in this field, it's for NTSC. Now the PIF is what determines this. So this is already figured out for us. If it's a 0, it's PAL, and a 2 is MPAL. And so here, then we can also determine if it was loaded from a 64DD or a game pack. Again, we're just going to step over all of these, whether we need them or not, because the game developer that follows us and uses our code may want to use these values. So we're just not going to touch them, and we're going to leave them as is. So the ROM base address for cart ROM or IPL. Again, I'm not positive what all of these are. So this is kind of nice. OS reset type. We can determine if it was a cold reset, a non-maskable interrupt, which is when they hit that reset button and then the PIF forces the console to reset. Basically, when the PIF hits that non-maskable interrupt, that means that it is going to reset. There's nothing you can do about it. That's that. Number 2 here is to reset to boot disk. I believe that is part of the 64DD features. So let's see here. Here's the CIC. Which chip in a given game cartridge was built into it. Here is a version number. I'm not sure. But again, we're going to leave these alone since we don't know them. This one is really a handy number. This is the official determination of whether it's a 4 or 8 megabyte RD RAM. So whether the expansion pack was installed or not. This is a little extra. The NMI buffer, if the game needs to save some values in memory, it can be written to this area, and it's considered safe. Now, from some of the things that I've read, the RAM is part of the CPU reset, so anything that's written here may not actually be there by the time the console has finished resetting and comes back. So I don't think that this data can be counted on. and that's why I'm willing to overwrite that. This was one of the so if you're familiar, Banjo Kazooie was supposed to be able to try and transfer some save game data over to Banjo Tooie so you could unlock new things, but they had some issues with, I believe it was this exact thing that they couldn't swap cartridges because Banjo Kazooie, between pulling out the Banjo Kazooie cartridge and putting in Banjo Tooie, it, it took too long just because it was a human doing it, and the memory would actually forget this stuff. So once again, we're gonna assume that that is not working. All right. So our goal is to stay within this 400 bytes. Not sure how successful we'll be. It's a good challenge, but technically we are safe, probably up to about 1,000. But smaller is better, and we'll see that. And if we can truly add some value for those extra instructions, I'd be okay with exceeding a 400 or 600. But 1,000 is going to be our hard stop. That is where the game code will start. So that's important. So throughout this little series here, let's see. Oh, we will assume that exception handlers will not cause nested exceptions. That is just going to get complicated. Once again, we want to write nice and simple things. If this is required, it will be up to the handler writers. We want to keep it just as simple as we can. All right. So lots of references here. There's some stuff going on. I'm going to go ahead and include this text file in the repository and in the Git repo. And so you can see kind of what is working. I've been looking at N64 exception handling for over 2 years and doing the research towards this project. So this is at least a year old. The things that I wrote here, lots of good stuff, but I'm still going to take a little variation on that. And then Peter Lemon has some basic interrupt code here as well. So this is just the last thing I kind of want to call out. When an interrupt or exception occurs, there is some overhead before it actually gets to calling your, even our interrupt or exception handler code. I'm not sure how many instruction cycles exactly, but that is something you can't necessarily control. What it takes, how long it takes the hardware to actually get to this point. So also you want to watch your instruction counts in general. So we'll count up all of the instructions in the handler, including ERET, which is how we're going to actually exit our exception or interrupt handler and put the console back into its normal state of executing game code. Now, this is one of those things here. Minimize the register usage in the handlers. Not all exceptions or interrupts require all registers to be saved. Save off all the registers in the custom handler. All right, so what that means, the most common scenario, the most common thing that I've seen done in these exception handlers is right at the top of the exception handler is they literally save off all 32 registers in the scalar part of the processor. Sometimes they'll save off the 32 64-bit registers in the floating point coprocessor, and then they'll do their work. And then they'll have to restore all of those registers to their known value, to their previous value, so that you can go back to executing game code. Now, the challenge and part of why I wanted to do this so bad is that means that every exception or interrupt that occurs has 64 store instructions and 64 load instructions. So that's 128 instructions without doing any work before the work is done. And that just seems excessive, especially in a system where you want to do the minimum amount of work possible. But again, we don't have a ton of resources here. You know, if you're if a game is running at 60 frames per second, which was not common, honestly, just not common. But if it is running at 60 frames per second, that gives you about 1.5 million CPU cycles per frame. That's not a whole lot. And so we don't want to use, one, two, three, even, you know, some of these things could be using a lot of that resource. We're going to try and minimize that, especially while we're figuring out what kind of interrupt or exception occurred. And then we're going to let the exception handler author actually do the rest of the register, save, and restore that's needed. And we may kind of help with that. Depends on how close we're doing on our instruction count and our range, our memory range. We'll see if it adds value. We may attempt it, but we've got some other cool things to do here. All right. So real quick. Usually I will code this live, but I knew there was going to be that whole upfront explanation. So I went ahead and wrote this in advance. This is just a exception test, and exception test, and so we've got our standard init, which I did go ahead and enhance a little bit. I initialized the stack pointer register. We're not going to use that quite yet, and we'll kind of get there, but I think that's a difference over the current status of the repository. All I did was read that memory value I talked about from 8,318. And that comes back with either a 40,000 or 80,000, and it is in hex. And then we do just a couple of operations to put it into the right RAM range, and it puts the stack at the very top of the RAM range. And we go ahead and subtract 4 bytes from that so that it can start writing immediately. So pretty basic stuff, but it's different and it's there. All right. So we do the init. We set up our screen. We're not even going to get to our screen in this example, but it's the right thing to do. And so then we've got a couple of nops so that we can see things, so that we can see the difference. This is kind of an interesting technique, these 2 lines here. So what I did down here at the bottom is I put a label and the instruction. What happens here is the ERET instruction gets compiled, and it's the actual instruction is put there, and it's got a label. So what we can do here, this is kind of one of those hacks of assembly language and using the assembler, but so we take the label and we load the address of that label into the T0 register. And then here we're going to go ahead and take the word value, because all MIPS instructions are a full word in length. And so it's going to load the word. It's going to take that address that we just loaded, and it's going to reuse the same register, which is fine. And then, like I mentioned, the handlers that we need the 8000, and then the general, the TLB and the general handlers. So this one, we just did the LUI, load upper immediate, which puts the 8000 at the top of the register in 32-bit mode, and writes zeros to the lower half. So we didn't have to use like the LA, which is going to load up both halves of that register. And then we store T0, which is our e-return instruction. We store that into that memory location. And then we take the T1 and we add that 180 to it, and we store that. So again, we're just writing this e-return instruction, and that's going to be the entirety of our exception handler, is just to exit back out. So pretty simple, but we're going to see how that works, and so that'll be good. And then here, we're loading the address. Instead of the 8000, I just went the 7000 range, which doesn't have any memory behind it. It's a bad address. And so we're going to attempt to write zeros to a bad address. And that should throw an exception. So we're going to see that. And then this other we're going to come back to, because this is an interrupt versus an exception. So first is in it the exception. All right, so we'll come over here, make and debug. All right, so this is loading up, and we're gonna jump, and this puts us right into our code. This is our initialization with our stack pointer. Now we have our video initialization block, and this is that code I was just talking about, where we're loading up the e-return instruction, exception return instruction. And so I set the breakpoint, so now we're down at the e-return instruction, and it is located at 1168. So we can scroll down just a little bit, and we see that's our instruction, and this is the memory address, and over here is the binary representation of that instruction. So we loaded that into T0, and now we are going to write it out to our two different memory locations, and we can go and take a look at that. 8, 1, 2, 3, 1, 2, 3, 4. And there's our e-return instruction, exactly as we expected. And there is our other one at the 180 mark. All right, so that looks just fine. Now we are going to trigger, and this is an exception handler. So this is an exception that we are going to trigger, and I point that out because interrupts have another step that has to be done before they will trigger the exception or interrupt handler. All right, so right now we're gonna store a 0 into this invalid memory address. I'm gonna hit F10 to step, and there we are. We hit our 8000 address. We've got our e-return instruction, and so this is going to return immediately. But what I want to point out, and this is way down at the bottom here, is we have the cause register. Actually, I'll point out that in red are the values that changed, and so this is a real benefit here. So we have the SR, The error program counter, and so SR is the status of the CPU, and so this is going to be what actually tells us the type of error that occurred, and I believe that's the 2 at the end of this. We'll look in just a moment at what that means. So EPC 1110. This is the actual store word instruction that had the problem. Here, let's type that in. And that is our store word where we tried to put a 0 into the 7,000 range. So, cause is what's going to actually tell us what went wrong, I believe. We'll look. So the count register, it always changes. That one doesn't really matter here. Entry high. This is part of the... what we triggered is the TLB exception. And we can see that here. TLB is on the 8,000 range. And so entry high, entry low 1, low 0, 1, those are TLB related registers. Also, I forgot to mention that all of these named registers here are actually in the coprocessor 0. So these are the ones that we're going to be interacting with in this series. And again, we can actually see a bad virtual address in the 7,000 range, as that's where we tried to write it to. So we'll take just a moment and let's see that the registers, yes, it was right here. Okay, so this is the status register, and this is let's see if I can tie this back. The status register is called SR in MAME, and so what I'm going to do is I'm going to open the calculator. I'm going to put it into hex mode. Doesn't really matter. Number 2. I know that the 34 is normal stuff, and we can look at that too. But I believe what we're looking for is the 2, which is the second from the end bit here. And so we come over here. The second from the end is the EXL. And that indicates an exception level. 0 is normal, 1 is an exception. So it's not really telling us a whole lot. In this case, the fact that we're in this 8,000 range actually tells us that it's a TLB exception and that we need to handle it as such. And so, let's see. Real quick, we can look at the 34. There we go. Here, I think I can fit these on. And again, I just want to be able to see these bits while I look at the data sheet. So let's see. The CU is the top 31, 30, 29, 28. The top 4 bits. So by default, CP0 and CP1 are enabled, and that's what we see exactly in these top 4 bits. And the next one down is the, let's see, it's the top 4. RP is 0. That's low power mode, not using that. And FR enables the additional floating point registers. Okay, So it enables up to 32 registers in the floating point unit. So that's what those mean. And that. So here's the other thing. Let's see. So this exception occurred. We know that it occurred on this EPC. One of the things that the MIPS processor, here we can see that the program counter is looking at the 8000, which is exactly where we're on here. But one of the things that we can't do is to actually directly assign to the PC register. That's kind of... It seems like you should be able to just assign to it, and you would do that. Well, that's kind of what the jump instruction will do. The jump instruction will assign PC and allow you to jump around. But when we're in an exception handler, we don't want to be jumping the program counter. So what we do is we actually, if we need to, and this is a case where we will, we can change EPC, and we could increment it by 4 in order to skip to the next instruction. But and then when the return instruction is executed, EPC will become PC. And so what we're going to see here is I'm going to do F10 to step and execute the return instruction. And what happens is it puts us right back at this store word instruction, which triggers again and causes the exception again. So it just loops because we're not fixing the problem that occurred. And so very simply in this scenario, we could increment the EPC to skip the invalid instruction and then return, and it would just move on to the next instruction, which would be the NOP, and then these. So we're going to go ahead and exit out of this. That is an exception that occurred internally because we attempted to write to an invalid address. Okay, so now we're going to take a look at an exception. So I'm going to comment out these 2 lines so we don't trigger that. And these stay the same because we're still using that return exception handler, for lack of a better term. It's really just the one instruction. And what we're doing here, so MFC will read... So once again, this is an interrupt that we're going to force right now. And we're going to force a timer interrupt, which, of all things, is actually still internal to the... so here... Yeah. So in this IM7 to 0, we have the interrupt mask field. Enables external, internal, coprocessor, or software interrupts. We set it to a 1 for enabled. So IM7 is the mask bit for the timer interrupt. Then we have the mask bits for the external interrupts, which are the 4 through 0. And those are the ones that we saw on the schematic for all of the different pins coming in. That's where those tie to. And then here we have mask bits for software interrupts and IP 1 and 0 of the cause register. Yeah, so I don't think any N64 programs use the software interrupts, but again, there's no reason for us to not support them. So we're going to be looking at those as well. So coming back to our code, the count register, acts as a timer, incrementing at a constant rate, half of the P clock speed. So the main CPU runs at 93.5 megahertz, something like that. So this counter counts up at 46 megahertz, basically, half of the main CPU speed. So that is the count register. And then in order to trigger the timer, we need a compare register. So the compare register is used to generate a timer interrupt. It maintains a stable value that does not change on its own. When the value of the compare register equals the value of the count register, interrupt bit IP7 in the cause register is set. This causes an interrupt in the DF stage as soon as the interrupt is enabled. Writing a value to the compare register as a side effect clears the timer interrupt. For diagnostic purposes, the compare register is a read-write register. That means that once you write a value, if you forget it or whatever, you can pull it back out. However, it is usually used as a write register, and it's just 32-bit number, and that's it. So here, what I'm doing is I'm going in and I'm reading the count register because it's always changing, and I'm gonna take a little bit bigger number, and I'm going to load that into the T1 register, and then I'm going to add the count plus my big number and write it out to the compare. So that makes the whatever the value that is in count makes it big enough that it'll take a little bit before the timer interrupt fires. And hopefully before it fires, we're going to do this bit, which is going to actually enable the interrupts, because otherwise it won't fire still. And that's why we needed to get a big enough number to get ahead of it. And that could still be that it's too big, but it puts us in the right place. So here we're actually reading out that status register, which is the one that we saw here. We're just reading in this whole big number, the whole value. And then we take that. And here we're going to load up. It's better to do this in steps. I just saw that I don't need this instruction. I can swap some registers. But we're going to look at it this step by step. So we're going to take this value, FF01, and load it into the T1 register. And then we're going to OR it, the T1 and the T0, back into T0, and then we're going to write this back out to the status field. So let's take a look at what this FF01 is going to actually do in that register. All right. So the FF is going to set all of the interrupt mask fields to enabled. And I could be more selective and only do the timer interrupt and so on. But for our purposes, I'm just going to turn them all on. So that's the FF. And then we have the 1. And so we look at the 1 position, and that's this IE down at the end. And this specifies and indicates global interrupt enable. So in order for this timer interrupt to fire, we technically need IM7 and IE in order for that interrupt to fire. And then, of course, the count and compare registers to match, and then our interrupt will fire. So this value just sets all of those interrupts to on and enabled, and with any luck, our count compare exception handler will trigger. So let's see if we can. All right, so that was our initialization, our video init, actually setting up our e-return instructions there. Here's where we started to do our count stuff. I'm going to set the breakpoint there, and we're going to kind of take a look. I'm actually, because I know 30180, I know our exception handler is located there. And here I can show that very quickly. 8123 0180. There we go. That puts our e-return instruction in the 180 and the 8000 range. So now we're going to operate. So we can see that the count 1B85B31. We're going to take that out. We're going to put that into our T0 register up here. And then this is the LUI-ORI is our load immediate for our big number, our million or something like that. And then here we add the million to our current counter and put it back into register 0. So if we look really close, here's 1B and here's a 1. So it's going to be 1C and then that other stuff. So we're going to let that happen. And there's our 1C number, which is great. And then we're going to put that into the compare register, which is right here, which is currently 0. And so we are going to assign that. And there is our 1C value. All right, so now here we can see that the status or SR register is 34,000 with the zeros on the end. That's not actively in an exception, so we can tell that. And so we're going to read this. We're going to read that 34,000 value out and put it into the T0. And there we go. And then into T1, we're going to put in our FF01. And then we're going to combine the 34,000 with our FF01 through the OR operation there. And then we're going to put it back into the SR register. And so now we can see that all of our interrupts are enabled there, and our global interrupt enable is set on as well. So now I'm actually just going to let this run. It's a million count, and we're emulating, so it's going to take a little bit to get there. So I just hit F5. Oh, that went quicker than I expected. Great. So we can see that we hit the 180. This is, again, our e-return exception handler. We can see that the count value and the compare value, it looks like count actually exceeded the compare, and that was what triggered it. A MAME emulation is excellent, so I trust that that is the expected behavior. And our PC is at 180, and our EPC is 1114. Oop. There we go. 11.4C. So it actually occurred on the jump instruction, which is our eternal while loop. This is where it jumps 11.4C, jumps to itself over and over and over again. So we know that we were sitting in the loop. We know that it was not the jump instruction that caused the problem. And we could look and compare our count and compare register values, and they were identical. So that is an interrupt that got fired while we were doing something else totally. And now we have the option in software to respond to that. All right. So this was kind of a big topic. Covered a lot of stuff, even just the basics of exception handling. Really involved stuff. I hope this made enough sense. But we're going to start some actual code stuff in the next video. Thank you.